Thank you. I'm George Halliwell, and today I'm going to be talking about progress on our Sandy Supplemental OSEIOSSE project, which involves taking our prototype OSEIOSSE system that we recently validated in the Gulf of Mexico, sending it into a larger Atlantic domain and test observing system impacts initially for I'm not advancing.
It's a single mouse click to make that window active.
Oh, single mouse click. Okay. Okay. There we go. Thank you. Okay. So our goal with this project is to develop and demonstrate a relocatable OSEIOSSE system in a larger Atlantic domain for a broad range of oceanographic problems, but the initial emphasis of what we're using it for will be observing system design studies for the purpose of improving ocean model initialization and coupled forecast models. The OSSE system, which was validated initially in the Gulf of Mexico, was developed by our joint Ocean Modeling and OSSE Center, and I list collaborators in this group on the screen. Topics for this talk, I'll just briefly mention what an OSEIOSSE system is for the uninitiated. That's a very short part. I'll briefly mention our new Atlantic Ocean domain. And the bulk of the talk will focus on evaluations of the OSSE system nature run and forecast models. Then we'll move to a full evaluation of the OSSE system. And then I'll show progress on initial applications toward hurricane-related applications. The OSSE system that we have incorporates all the design criteria and rigorous validation methods that have been developed for atmospheric OSSE systems. Primary components are nature run, which is stipulated to represent the quote-unquote true ocean. And in our case, it's a HICOM run, it's very high resolution, 3 to 4 kilometers in our Atlantic domain. Data assimilation system, the ocean model, which we call the forecast model, is also HICOM. We have a substantially different configuration from the nature run, so that it behaves very differently from the nature run. That's the key requirement of an OSSE system. And also, an important part of the system is a toolbox to simulate synthetic observations from the nature run. This involves adding realistic errors, the same errors you would actually have in the real observing system in the ocean. You have to simulate that in the samples you take from the nature run. The new Atlantic domain is shown here with the important application, hurricane-related applications, of course, we include the Atlantic hurricane region. And regions impacted by hurricane are located far from the boundaries of the system. But as time progresses, we'll be looking at other applications in terms of evaluating observing systems. For example, spreading of the Amazon River plume, regional and coastal applications in the Gulf of Mexico, et cetera. But our initial work has been done throughout the hurricane domain. There's no requirement to memorize this. I just want to go through the what we did to make the nature run and forecast models work differently. First of all, on top, they run at different resolutions, 0.0 degree Mercator for the nature run, and half the resolution for the forecast model. There are more vertical layers in the nature run than the forecast model. Use different bathymetries. There's a higher resolution product recently developed at NRL that the nature run uses, but not the forecast model. Forecast model, forcing is obtained from the same atmospheric model, but we're using 3-hour fields for the nature run, 6 hours for the atmospheric forcing. And a very important difference is that the two vertical mixing schemes use KPP in the nature run and the GIS level 2 Victorio Canuto in the forecast model. And these models behave quite differently and then help us get different behaviors, characteristics of these two different models. Other parameters are set differently, as you see. To successfully evaluate the nature run and forecast ocean models, to demonstrate that we have a credible OSSE system, we have to have several. We have to achieve several criteria to be reasonably sure of that goal. First of all, the nature run has to realistically simulate ocean climatology and variability. It doesn't have to be perfect, but it has to be sufficiently realistic that to give you confidence that you're sampling something resembling the true ocean. It's not exactly that. The forecast model must be a less capable model, but also cannot be too unrealistic. The comparative performance between the two models has to also satisfy several criteria. The fundamental criterion is that the error growth rates between the nature run and forecast model and unconstrained runs of these models resulting from different physics and truncation errors must be similar to error growth rates between the best ocean models and the true ocean. That's a specific statement, cannot be rigorously evaluated. We don't have perfect measurements of the true ocean to be sure of that. Therefore, in comparing the two models here, I use what I call three less stringent criteria. First, I will show that initial RMS error growth between the two models reaches saturation levels within a realistic time interval. Second, when error saturation is reached, the RMS error levels, the levels of RMS error differences between the two models are very similar to the error levels between the nature run and observations. If that's not true, if the errors are much larger or much smaller than the typical errors between the ocean models and the ocean, then you're going to likely get biased OSSE results. Also, I'll demonstrate for the third criterion here that mean biases in the forecast model with respect to the nature run have similar magnitudes to mean biases in the nature run with respect to observations. Now, we don't achieve exactly, but I'll show that we, at least in many of these criteria, this first attempt at a nature run that we produce is at least sufficiently good for us to perform our first round of OSSE. Of course, research on improving a nature run is ongoing. Ocean models are not perfect, so part of our work is for future OSSE experiments to further improve the nature run so it more closely resembles the true ocean. To show evaluation results here, we performed a prototype nature run from 19 September 2008 through 7 October 2013. This run is unconstrained. We terminated at that time because there was a major change in the high column analysis product, which we use for boundary conditions, a change to force into a new atmospheric model. So we decided to just rely on a 5-year period for our first round of OSSEs. For the evaluation, we performed an unconstrained forecast model simulation over the same time interval, so we compared the two models and see if they satisfy the criteria I discussed previously. These models are initialized from the same fields, global HICOM, so we'll be able to look at the error growth between the two models after these runs begin. Now, time series, because the ocean variability varies a lot in the horizontal direction, we separated this time series analysis of the error growth into 4 regions, which are shown here: the Gulf Stream region, Atlantic Hurricane, west and east. That's separated because the variability is much less energetic in that eastern region, and the equatorial region. So how do errors grow between the two models? They're shown for the 4 regions, as color-coded is shown. On top, there's correlation coefficients between maps of sea surface height, and on the bottom, the RMS error between the two models in sea surface height. And you can see the initial error growth occurs during the very first few weeks to 4 to 5 months. There's no way to say if that's exactly the way the rate that errors grow between ocean models and the true ocean, because we cannot initialize an ocean model with the true ocean. But our assessment is that that error growth is at least qualitatively realistic. There are no red flags there that make us think that realistic errors are not growing between these two models. So the evaluation that I will perform and show in the subsequent figures will focus on the 4-year time interval outlined after the error levels become saturated, and for exactly 4 years, so that annual cycles don't alias our results. Okay, so the evaluation criteria, I'll be looking at maps of mean climatologies from both models. I'll compare those to observed climatologies. And then comparing the two models in terms of their climatological means, the performance criterion I'm looking for is that are the biases between the nature run and forecast model realistic, similar in magnitude to biases between the models and the true ocean. So I'll be comparing mean climatology in each model to each other, and actually I'll be calculating biases, looking at the difference between the nature run and observed climatology, the forecast model and observed climatology, and the difference between the two models. Now these should be similar in magnitude if we have a reasonable nature run. In terms of the variability, I'll be comparing model RMS amplitude maps to RMS amplitude maps derived from ocean measurements. And to compare the two models, I'll be looking at RMS difference maps, nature run versus observations, forecast model versus observations, and then between the two models, just to see if differences between each model and observations have similar magnitudes to those between the two models. So if we pass the test reasonably well, then we can declare we have a usable nature run. So first, I'm going to look at mean dynamic structure represented by model sea surface height. On the upper left is the mean SSH from the nature run. Second down from the left is from the forecast model, and on the bottom left is the mean dynamic topography determined by a VSO. And basically what you see here is that for the differences in the means, nature run minus a VSO and forecast model minus a VSO, these are the differences shown. The differences between the two models, as you can see, is smaller. So it really, this comparison is a little bit disappointing because I'd like to see similar magnitudes of differences. But I want to point out that this is for SSH, and SSH is strongly controlled, of course, by the mean SSH is strongly controlled by the mean wind stress curl pattern. So what I want to do next is to look at what's happening below the ocean surface, because there I'll show that differences in mean biases more satisfactorily solve or agree with the criterion. So let me move to...
George, on that plot, I would conclude that the forecast model is too close to the nature run.
Right. Oh, yes, that's exactly what the point I was trying to make. But that's for SSH only. I'll show for other fields, especially subsurface fields, that they're not as close. Like I said, the mean SSH pattern, the gyre pattern, is largely a function of the mean wind stress curl forcing. So you'd expect more similarities there, but the ocean is adjusting quite differently beneath the surface in the two cases, which helps us. And this is the mean dynamic structure of the depth of the 20 degrees Celsius isotherm. So here we're looking at more about how the model is adjusting beneath the surface. And if you look at the differences between the mean bias, nature run versus odds, FM forecast model versus odds, and between the two models, here we see a closer correspondence with the criterion we're looking for. The bias between the two models is slightly less, but it's much closer than we saw from SSH. So this is a much more encouraging result. Now, for the surface or near surface velocity, we have the climatological fields were conducted by Rick Lumpkin with the surface drifters. So here we have mean climatologies of current speed from the Nature Run forecast model and from the drifter data set. And if you look at the difference maps between the three, again, we see regions where we have comparable differences here and here. I would still argue, though, that there's perhaps a little bit difference is still a little bit small compared to the between the two models compared to differences between models and observations. But again, I will emphasize that Nature Run is developing nature runs and improving nature runs in the future is part of our ongoing work. So we'll be taking these results and devising plans, schemes to see if we can further improve nature run performance. This is now the mean thermal structure of sea surface temperature. Again, the surface variables are strongly controlled by the atmospheric forcing, and tend to see in the differences between the two models tend to be somewhat smaller than the differences between each model and observations. But if we look between the surface, where we look at temperature average between the surface and 100 meters, the differences are still perhaps a little smaller than we'd like, but they're closer to the differences between models and observations. Okay, now we'll move on to the dynamical variability. And the RMS maps of sea surface height, two models shown on top, and from the VISO are shown. Generally, we see, with the exception of the circled region and the Gulf Stream extension, the models are underestimating SSH amplitude. Correspondence is generally quite good, and we see in terms of RMS variability levels, say in the far western Atlantic, east of the Bahamas, we see better performance in the nature run compared to the forecast model, which is a factor of the higher resolution and larger energy present in the nature run. Now, the region in the Gulf Stream extension is particularly bad, but we're not focusing on that region now. We'll be focusing primarily for hurricane problem on the Atlantic interior. I think there the comparisons are better. Now, going back to the drifter data set, we can look at the variability in zonal and meridional velocity fluctuations from each model, nature run on top, forecast model in the middle, and from the drifter data set on the bottom. Generally, in the interior Atlantic region here, the levels are fairly comparable. You tend to see sharper maxima in the model compared to the values conducted in the drifter data set. But one thing you have to consider in the comparisons between the models and the observations, one factor here is, of course, the models run a higher resolution. We're looking at only a 4-year mean, whereas the drifter data set that is over a longer period and is substantially more smoothing. If you take all of that into account, I don't think these comparisons are that bad. Obviously, as we run longer nature runs, we may get more smooth model results or compare better. But okay, I've been showing comparisons over a 4-year time interval. But for the hurricane problem, we're going to look at specifically during hurricane season and look specifically at some hurricane-related metrics. Here I'll bring in some observation-based products derived from satellite altimetry and the SST, specifically the depth of the 26 degrees Celsius isotherm, the 20 degrees Celsius isotherm, and tropical cycle and heat potential. There are two sources that I use herein for AOML and Rasmus. But I'll be looking at first the depth of the 26 degrees Celsius isotherm. This is during 5 hurricane seasons. only. So what we see on top is the RMS difference between the nature run and the observations from the AOML product at the upper left. And here we have the difference between the nature run and the Rasmus-derived product. On the upper right and middle right, we have the same field for the forecast model. And here we have the forecast model versus the nature run. Basically, the difference fields between the two models is either comparable to or slightly or a bit smaller than the differences between each model and the observation-derived products. Again, we like to see the nature run have a little bit more variability, but at least we're not super far off. Yeah.
What were those units there? Is that meters?
This is H26. Yeah, it's 10 meters. Oh, yeah, it's plus or minus 50 is what the scale is.
That's huge, right? Difference of 50 meters and the depth of 20%.
Yeah. That's right. And of course, this is during hurricane season when we're looking at that depth being maybe, in the hurricane region, maybe between about 50 and 150 meters. So, yeah, these are significant differences.
Do you have a difference between the AOML and the Rasmus?
No, I include both.
No, we computed that. I just don't remember how to look at it. But we did compute the difference, exactly what you wanted between the two data sets, because you can tell that they have also their own differences.
Exactly, yeah. And it's a matter of what the point I want to make with that is that observation-derived data sets are not perfect. There are going to be differences between the different ones, and it's not a statement of whether one is better than the other or anything like that. It's just that there is uncertainty in these observation-derived products just as much as there is between the two models. So.
I think one conclusion from that comparison was that it was hard to tell because it was regional. So many differences were regional. It was not like one is like, higher value than the other altogether. It was hard to be confused.
Well, just another question. So most of the hurricane models are making in the bottom bigger forecast model is nature, and most of it is blue, right? So which
Yeah.
one is more? So one of those two models is consistently making H26 deeper or shallower than the other.
Oh, it's FM. Forecast model is shallower. Yeah. Yeah. Again, it's probably the two different mixed layer models that we're using are giving those differences, primarily giving those differences. Now, for the RMS variability, actually the comparison is actually quite good. This is RMS, RMS sampling, not the RMS differences. So the variability of oh yeah, this is the differences in the means. I should point that out. Yes, and this is the RMS differences, and those are quite. Comparison is actually quite good. The difference field between the two models is quite consistent with the differences between each model and either of the products. So this is probably one of the most encouraging results in terms of the nature of all the ones I've shown so far. Now, if we look at the mean bias in the 20-degree isotherm depth during hurricane season only, and here we were only able to obtain the 20-degree isotherm depth from the Rasmus product, which is shown on top for both models. But the differences between the two models a little bit smaller, but not too bad in comparison to the other differences. And the RMS magnitude generally fairly good, perhaps slightly smaller between the two models, but overall not too bad. So I guess the overall conclusion is that well, first of all, we basically had to proceed with our first OSSEs with this first nature run. I've shown a number of areas where we still need to improve the quality of the nature run. At least it's not, we're at least in the right ballpark, although there tends to be some underestimation of mean bias and RMS errors for some variables. We'll be working to reduce those differences for future OSSE work. Now, I'm going to mention now the OSSE system evaluation, where we compare OSSE and OSSE pairs, OSSEs being using assimilating real observations, OSSEs synthetic observations. We'll compare experiments that are identical, except for one assimilating real and one assimilating OSSE, or synthetic observations. And if we get similar impact assessments between these pairs, then we can demonstrate that the OSSE system is producing credible impact assessments. So we have pairs of experiments. On the left, we have the various observing systems we're assimilating. There are two OSSE pairs that we run. The difference is between the control and the other experiment, we deny two altimeters. The control assimilates all observations, except for one that's withheld for evaluation, in which case the Argo floats. Here we deny two of the three altimeters. The second pair, the control experiment, assimilates all observations except ship FCT profiles, which are withheld for evaluation. The difference between these are we deny the Argo profiles. Now, the question is, do we get similar results between each pair of experiments? And the answer is generally yes, where we have, or let me orient you in these figures. For example, the upper left panel is for the depth of the 20-degree isotherm. RMS error shown on the level shown on the left, and this is with respect to the Argo floats that were withheld for evaluation. And for the free run, we have this error level shown in black. For simulation of one altimeter shown in red, and three altimeters shown in blue. And we have several variables, three variables in the Atlantic Hurricane West region, 20-degree isotherm depth, the mean temperature of the upper 100 meters, and SST. Here we see some impact where we have RMS levels, error levels that are somewhat too small in the nature run, and that shows up in these cases here. The bottom three panels are the same three variables in the Gulf Stream region. But perhaps one of the most important point in terms of evaluating the overall OSSE system is that we're generally getting similar impact assessments, with OSSE shown on the right and OSSE on the left. And that's generally true across the board, although we have a significant difference here in the Gulf Stream region for the average temperature over the 100 meters in particular. So generally, these are encouraging, but again, not perfect. And when we improve nature runs in the future, presumably these comparisons will improve.
The SST, that seems like a huge difference.
Yeah, no, and here. Okay, well, see, we're getting similar assessments here, but significant difference in the RMS error level. Here, it's a larger difference, you're referring particularly to this in the Gulf Stream region, right? And that is true. So, yes.
I think I'm lost.
Okay.
And because I'm lost, maybe somebody else is lost. How did you compute the RMS? I mean, you've now shown spatial maps of the different...
Oh, these are profiles extracted from the experiments compared to Argo float profiles. These are real Argo float profiles for the OSEs and synthetic Argo profiles for the OSEs.
The average difference between the nature run and the...
It's an RMS difference over the entire profile and overall Argo
this is
profile.
an evaluation of the forecast model.
Yes.
So the forecast model versus Argo profile, there are 80,000 of those or something like that on the time period that you're talking about. And the mean RMS, average difference between those.
Right, the RMS, right.
But is the difference in analyses or forecasts?
Oh, these are all analyses.
Oh,
Yeah,
okay.
that's our year forecast. Yeah, don't want to confuse that.
Yeah, so this is the impact at analysis time of real Argo flows versus, from the real ocean versus synthetic Argo flows from the nature.
Well, they're used here for evaluation only in this case. They're withheld in both cases. And
right. But the ones from the nature are synthetic, they're pretend or imaginary, hypothetical Argo. can't.
Oh yeah, they're synthetic, yeah.
Right, you can't compare the nature run to real argo flows. Those are totally different.
Right, exactly. So we're looking at this in a statistical sense. Do we get similar error reductions due to assimilating either one or three altimeters? And the answer is we don't get the exact answer, exact same. We have cases where the comparison is fairly close, but others where, for example, mean temperature, we're getting perhaps more favorable results in the OSSE compared to the OSE.
Right, so from the synthetic data basically seems to have a more positive impact.
On average, yes. You look, there are cases where it's there are cases where it's closer. It's particularly close in the Gulf Stream region for H20, but more so than others. So there's some bias towards.
Actually, that's the point I would make here.
Okay.
George, I think the key point is that your forecast model is too close to the nature run, and because of that, you're in between a fraternal twin and an identical twin, and so the results are too optimistic in the OSSE right now. And you talk about improving the nature run, but the nature run should represent state of the art. You can't improve that until our modeling improves. You can make the forecast model further away from the nature run, and that might solve the problem.
One thing is that you're actually using a different atmospheric force.
That's probably key because.
This one now, so
Yeah.
so then because as George mentioned, those really bad effects on the surface.
And particularly if surface fields were close. Yeah.
So that is almost completed. So this is like part of your kind of showing the methodology, but in the meantime going back and redoing.
Yeah, but to the question of whether or not this validates the OSSE system, I would answer no. So there's more work.
More work.
But it would make the innate run and the FM different because it would have to do with it.
Right, but this particular system doesn't quite meet the criteria.
Yeah.
Now for the second pair, where we have compared free run without Argo and with Argo. And actually for H20 here, the comparison is probably much better than some of the others I've shown. But for the mean temperature of the upper 100 meters, it's somewhat more optimistic results from the OSSE side. For SST, now here we have the XBT data has been withheld for comparison. So that's why, let's see, that panel should not be there. So let's just focus on A, B, and C. For SST, there's really no detectable improvement by either simulating the altimetry plus with altimetry without Argo or altimetry with Argo. I should point out that you can detect a very slight improvement by assimilating Argo, but I'd argue that's not necessarily statistically significant. I'll return to that point later. Okay, in terms of OSSEs, there are two categories of OSSEs that we are going to perform. The first are what I call the seasonal OSSEs, and that's what I'll talk about today, where we look at observing system impacts on pre-storm ocean model initialization. And here our intent is to evaluate enhancements to existing ocean observing systems, like deploying gliders, floats, or mister chains that are out for part or all of the hurricane season, not just prior to a storm. And these OSSEs are performed with a daily update cycle and a data assimilation. This is the standard procedure for operational systems. And it uses our existing 5-year nature run with analyses archived daily. Now, I won't get into this today, but we'll also be performing storm OSSEs where we look at the impact of observations within a near storm. But near the ocean responds so rapidly that daily update cycles are not feasible. So we're developing our system to be able to use very short update cycles for that type of work. And I won't talk about it anymore today, but that's one of our major plans in the future. Okay, now, I'm going to look at an example of a seasonal OSSE. And here I have generated synthetic glider profiles from the nature run. for 14 gliders, and they basically follow the typical step ladder pattern that was, for example, planned for the VHOD glider project. The two gliders shown in red are closest to the ones that VHOD deployed. But in this OSSE test, I'm doing 12 additional gliders to get a better idea of how the larger scale patterns can be potentially corrected by these observations. And the result was a little bit different than I expected. Basically, for the test of the 20-degree isotherm, here I'm showing in black the RMS error. It's calculated over that entire box that surrounds the gliders here. And the RMS error is calculated over all the model grid points within that box. For the free run, you see the RMS error levels shown on top and the mean bias shown on the bottom. The control run, which denies gliders, is in red, and the run that assimilates gliders is in blue. And basically what you see is no significant impact. If you look at the tropical cyclone heat potential, you basically get the same result. And this kind of surprised me. One thing that was surprising is that we saw solid impacts from temperature salinity profiles in the Gulf of Mexico. So why is this different?
George, so
yes.
There in this previous slide, so you put all the other observations except glider. Is that right?
No, this is compared against the nature run, directly against the nature run. So no, this is OSSE only. So we have these are RMS errors.
So you have all the other observations. I think that's the question.
Yeah, you have a synthetic observation.
Oh yeah. Oh, exactly. Yeah. Exactly. All observations are assimilated except for gliders in the red case, and then all observations, including gliders, in the blue case. So the control run, you see the error reduction in the control run. That's due to all the other observations that are assimilated.
Taking over the whole model domain.
Over the box that I show there, right?
So it would be good to look at is what happens if you only assimilate the glider, right?
Oh, that would go. There you would not have the other correction. My guess is, I haven't done that yet, but my guess is you would probably see a positive impact there because the errors would be so large to start with. I believe I looked at that in the Gulf of Mexico, that profile impact, if you don't assimilate altimetry in particular, you see more. So we're trying to improve over the existing improvement we get from altimetry, and that seems to be harder to do based on these results so far. In the Gulf of Mexico, for tropical cyclone heat potential, we showed this basic result, where in black, that is the RMS error time series from analysis runs, assimilated all observations, but no XCTD profiles. And the two other cases shown are, the blue shows the error reduction when you assimilate XCTDs at 0.5 degree resolution shown on the bottom panel. And in red is the result where you assimilate at 1 degree resolution. It should be every other grid point in the bottom panel. And as you can see, as you decrease resolution, the error correction decreases substantially. So this is not inconsistent. I mean, this is not inconsistent with what I just showed for the full Atlantic. We're looking at gliders separated by several degrees. And if you look at this, you might get the impression that if you go to 2-3 degree resolution, that you're going to have eventually have very little error reduction. So I can't say that what I see in the open Atlantic is inconsistent with what we saw in the Gulf Stream. Now, just one other item, and this actually goes back to Renel's point, that we actually do, with this glider run, see some improvement in sea surface salinity. Because sea surface salinity error is very large, it's not corrected in any substantial way by altimetry or other observations. So here you see RMS error reduction on top and a bias reduction that occurs also. So if you start with large errors, you can still see correction. So I wanted to further understand what was happening. So I decided to perform several idealized experiments within the box shown, where I simulate 1,000-meter CTDs, synthetic CTDs, released in a regular grid pattern for 30 days beginning 1 August 2009. And I'm looking at experiments with 4 different resolutions. I've simulated, taken every 5 by 5 degrees, 3 by 3, 1 by 1, and 0.5 degrees. These latter 2 cases would approximate what we did in the Gulf of Mexico region. So I want to see if we can see consistency with the Gulf of Mexico results with this set of experiments. And again, statistics are calculated by comparing the forecast model runs with the nature run and at overall grid points within the box containing those synthetic CTDs. And for the depth of the 20-degree isotherms, on top in black we have a free run showing the larger RMS errors. The red is a control run, assimilating all observations but not assimilating any CTDs, and that's shown. You see the error level here. And for the 4 different resolutions, you can see that for 5 degree, 5 by 5, and 3 by 3, you don't see any improvement over the control run. But when you get down to 1 degree resolution, 0.5 degree resolution, we're seeing substantial error reductions. And so that is generally consistent with what we've seen in the Gulf Stream. For TCHP, it's basically the same result. With a 1 degree resolution, we're getting measurable improvement, 0.5 degrees, yes, but not so for the coarser resolution sampling. And as you can see, this is Gulf of Mexico results directly compared for TCHP to the open Atlantic results, and qualitatively consistent results. So, and then very quickly, I'll just look at the results for 3 or 4 other variables. And again, it's the 1 degree, 0.5 degree results for mean temperature over the upper 100 meters. You see some improvement in mean bias in this case too for the higher resolution experiments. And basically similar results for sea surface temperature. And another variable of importance to hurricanes is the difference in temperature between 0 and 100 meters. That's roughly crudely represented as the mean stratification in the upper 100 meters, which is an important factor in how the mixed layer will deepen under hurricane forcing. And that difference is substantially corrected with high resolution profiles also. So that's an important result. And for sea surface salinity, basically, primarily, we see some corrections for the coarser resolution, very large corrections for the high resolution CTDs. That's again because of the large SSS errors that exist in the ocean models when they're not without assimilation. Okay, so with our system right now, we're only seeing ocean profiles that will have significant impact only if they're sufficiently close together. If they're separated by equal to or less than 1 degree, we see quite a bit of error reduction. But 3 degrees or larger, little or no impact. For somewhere between 1 and 3 degrees, we seem to lose most of our ability to correct the system. This is consistent with our earlier Gulf of Mexico results. And it's also consistent with the results from the 14 glider experiment, which were separated by several degrees, so it was very difficult to see any correction. We do understand why these impacts are limited to low resolution, because other people conducted OSE studies to detect impacts from Argo floats, for example, which were fairly widely separated also, and they were able to detect some instruments. However, these studies, because they don't have a representation of the true ocean, often rely heavily on error reduction in observations that were assimilated, which in the case of our OSSE system, we have a representation of the true ocean, and we're not restricted to that. So how much difference in our results is a factor, results from that factor, really we need to learn ongoing research. Okay, what is limiting the impact? And I'm going to look at the evolution and an animation loop here of differences between 2 experiments. One, in that this is the idealized CTD experiments. One where the profiles were denied. The second where CTD profiles were assimilated at 5 degree resolution. And okay. There we go. Let me backtrack here and stop this. I'll proceed systematically through this. Okay, at the first time after the first daily assimilation cycle, this is the correction you see. Basically, this is the difference between the experiment that assimilated 5 degree resolution CTDs and those that did not assimilate CTDs.
What else is being assimilated besides your synthetic CTDs?
I had the list earlier. 3 altimeters, various SSTs, MCSST products, satellite products, and drifter SST, ship SST.
And any subsurface profiles at all?
The ship XBTs are assimilated.
So you do have sort of the main thermocline is defined either by altimetry or by
Right, right. That's the starting point, right. Now this is the difference. This is the difference that shows up when you add the CTD assimilation. And so basically you see corrections, additional corrections are resulting from, and this is just the correction resulting at the first time step. And you see it looks reasonable. You see the radius of influence of the observations clearly. There are points where this is the depth of the 20 degree isotherm, so it's correcting depths that are either too deep or too shallow. So what happens as the assimilation progresses? What you see very quickly is a huge small-scale variability differences between the 2 runs form, and where you no longer can see the smooth corrections. So, this is a sort of a new result. There's really nothing in the literature that does this kind of comparison because nobody has an OSSE system quite like ours. So, understanding this is, I think, going to be important because all this very, very small-scale variability. And you're looking at maybe several tens of meters in the difference in the depth of the isotherm occurring along frontal boundaries. So there's a lot of small-scale noise in the system, which may be making it difficult to actually detect improvement. So what is causing this and how we get around it is probably an area of research. Okay, what next steps can we consider? The impact of that small-scale variability I showed may be hurting things. Now we're going to try comparing, calculating the errors after smoothing that small-scale variability. Obviously, we're getting corrections, at least on the eddy scale and larger, mesoscale eddy scale and larger, and see if it is that small-scale noise that's really limiting our ability to correct the model. We also need to further study the impact of our data assimilation system settings. The localization radius of the observation to limit how far away the observation could be before. And also we specify background observation error matrix in the DA system. Can we improve our ability to have these observations improve the model if we play with our data assimilation system to improve that? That's an ongoing area of research. Also in the future, we're performing OSSEs for individual hurricanes using the high-frequency data assimilation system that I mentioned earlier. We're also going to be looking at evaluating strategies to improve altimetry assimilation by improving the accuracy of synthetic profiles. And we intend to further expand the OSSE system. But the most important result here is this is like I said at the beginning, this is a progress report. As we proceed, we're identifying flaws and problems we have to solve along the way, starting from the nature run and other models, and then trying to understand what is limiting our ability to detect impact.
Well,
Yeah, this is B. Yeah, right.
Does that mean you're not just assimilating sea surface height anomalies?
No, we're actually using a Cooper-Haines adjustment in the vertical. But you know, for example, Gustavo has techniques to presumably more accurately project temperature salinity anomalies based on altimetry, and we want to bring that into the system and see if we can improve that. So I'll be working with Gustavo on that in the future. Anyway, so warts and all, there it is. So I'll take questions then. Let's see, Bob didn't see this. You missed the animation loop that I showed, right?
I can see it.
Okay. Okay.
So George,
yes.
You're suggesting that we fly the gliders in parallel, separated by 1 degree, right?
Well, you're likely to more accurately correct the model in the region between the two. What basically the result we're showing here is that the observation, the spheres of influence of the observations basically have to overlap before you see real detectable improvement in error reduction overall. If the observations are separated and those spheres of influence don't overlap, then we just get large errors forming in the small-scale errors forming in the regions between the observations. Yes. Oh, exactly. I mean, there you have you basically in the data system, you set the background observation error matrix. So you build into that, well, this observation we know is more accurate, so you get out a smaller error than ones that you know will have larger errors. So you reweight them in that manner.
So how did you weight your subsurface bogus altimetry observations to get everything versus the in situ glider observations?
Oh, they have the same weight in these experiments. I did not.
That's probably why you're generating all the small scale.
So we have a lot of experimenting. We have a lot of research to do to make sure we're doing it right, doing everything well. And any other questions?
To use that model, also model for the person model initial application, then you will need only for like 7 days. You're not going to do this more than 7 days. So it's 1 month.
Oh, I mean, for forecast will be
within 7 days. So does it really, is that a problem within the 7 days? That small scale error or is it something that show up?
Well, the basic problem is that if you don't see significant differences in the initial fields, then you're not going to really see differences in forecast. Will just be probably stochastic, not due to initial error reduction, hopefully improving the forecast. So I do point out that because of all the issues we're facing, this is not the final word in all this. So, anybody else? Anybody? At least I didn't hear any snoring. So. Thank you.
Let me know what you want to do, Peter.
Okay. What about yes?
So I'm going to give the same presentation there in Houston.
Oh.
That'll be the